Okay, this is a very short little introduction to something known as the Pythagorean Theorem. A theorem in mathematics is a statement that can be proved to be true, and the Pythagorean Theorem is a theorem or a fact that was discovered by the ancient Greeks, attributed to Pythagoras or one of his followers in the Pythagorean society. There's some indication it might have been known earlier, but this is the traditional interpretation here. The Pythagorean theorem is named after them. What it allows us to do is to take a right triangle, and a right triangle is a triangle that has a square corner down here. That's a 90-degree angle, or it's called a right angle. And if you take the two sides of the triangle that meet to form the right angle, these are called the legs. So this side and this side are the legs. And this side is given a fancy name. It's called the hypotenuse. Hypotenuse. That's an N-U-S-E. Okay, the hypotenuse is this diagonal side here. Okay. What the Pythagorean theorem tells us is that if we take the two legs and we square those lengths and add them together, that'll be the same as the square of the hypotenuse. Let's see how that works out. So squaring a number is multiplying it by itself. So take 12 squared. Indicate 12 squared with that little 2 there. That just means 12 times itself, so there's two 12s multiplied together. Comes out 144. You probably remember that from your multiplication tables. 16 squared turns out is 256. Let's pull up a calculator. Okay. Let's just see. 16 squared. X squared, there's the key right there. This is a scientific calculator, by the way, which has some of these keys that we need. So x squared, 16 squared is 256. Okay. And if I take these numbers and add them together, we get 256 plus 144. So I'll go plus 144 is 400. All right. So what is this length? Well, whatever it is, its square is 400. And if you think about it a little bit, you might realize that 20 times 20 is 400. But if you don't happen to notice that, you could just take your 400 on your calculator and look for the little square root key and hit the square root, and it'll tell you it's 20. Okay? Let's clear that. Now, we can also use this backward. What if we know the hypotenuse ahead of time, and let's say this is 20, and say we know this is 12, but say we don't know that this side here. And so we say, all right, what is this leg? So if you know the hypotenuse and one of the legs, how do you find the other leg? Okay, so let's do a new calculation. Since we know that this squared plus this squared gives us this squared, it turns out this squared minus this squared should give us this squared. So let's try that. So we take 20 squared and then 12 squared, and then we're going to subtract. Well, 20 squared we know is 400, 12 squared is 144, and then let's just subtract 400 minus 144, 256. And so this answer here is going to be 256. And so this length squared is 256. So I take my 256 and say square root. Say what squared gives me 256? It comes up 16. Okay? So this would be 16. Bottom line, for any right triangle, if you know any two sides, you can find the third side. If the two sides you know are the two legs, you square them and add them together and take the square root. If one of the sides you know is the hypotenuse, you square it, take the side you do know, whichever one it is, square it, and subtract, and you get the square of the other side. Take the square root, you got the third side. So let's look at a couple of ways that we can prove that the statement is true. Here's the first of several proofs of the Pythagorean theorem. what we have here is a right triangle whose sides are A, B, and C. A and B are the legs, C is the hypotenuse. And what I have over here are 4 copies of that same triangle. So that's 1, 2 here, and 1, 2 here. And notice the short side is labeled A, and so here's A, and so the area of this region, of the light region here, is A squared. And this is B, which is the same as this length here, and so this light region is B squared. Now, I call this the furniture and carpet proof, because if you realize if you have a bunch of sofas and chairs and so forth, and you just shift them around, you're not going to change the total area of carpet that shows through. You're just going to rearrange where the carpet's available. So if you want to create a dance floor, you might want to shove all the furniture to the back of the room, but it's going to be the same total area to start with. Okay? Well, notice what happens if I simply rearrange the furniture. This carpet has a total area of A squared plus B squared at the moment. But if I simply move the triangles in this way, what we now have is a square whose side is the length of the hypotenuse, C. So the square here is C squared. So guess what? A squared plus B squared is equal to C squared. Okay, this is a very nice proof, but it requires one little piece of knowledge from geometry, which is if you were to take a square and shear it, in other words, move the square parallel, or slide the square parallel to one of the edges. Okay, it's like you take a stack of playing cards and you slide all the cards to the side. You haven't really changed the area of the end of the deck. And so in this case, this parallelogram is the same area as the original square. Okay, well, let's run the whole demo now. And so it turns out that if I can shear this red square up to that position and shear the blue one, they'll slide down and exactly fit down here. Now what we've done is we've taken literal squares built on these sides A and B, and we've shown that the area of this square plus the area of this square equals the area of this square. Okay, so A squared plus B squared is equal to C squared. And so we can use it algebraically, just taking these numbers, squaring them and adding them together, and taking the square root. We can actually take the areas of the literal squares and do the same thing. Here's another proof. It's called a proof by dissection. What that means is cutting things apart. And so what we're going to do is simply cut and paste. We're going to slice this square parallel to the edges of the big square here. And we can rearrange it. And guess what? It all fits perfectly. Okay, let's do this one more time. If we change the shape of the triangle, the same thing is going to be true. This triangle stays a right triangle, by the way. So A and B are the legs, and A squared plus B squared should still equal C squared. And if we slice and rearrange, you'll find that that still stays true. Okay, one final demo. Let's just run it. And what we're going to do is slide up the large square that fit the hypotenuse. So here's C squared. And we're going to show that the red and blue regions fit exactly inside. We're just trimming off all the excess and showing that it all fits back together again. Amazing. It is an amazing theorem. It's amazing that this was discovered so long ago in ancient Greece, and it turns out it's one of the most fundamental theorems in all of mathematics.